Greeting, sorry. Greetings, my good and faithful students. Welcome to this special online edition of ME 573. I am your host tonight, Rooster the Great, and I'm going to be talking about discretizing the one-dimensional heat equation. This is the subject matter of, I believe, project number 4. And I intended to go through this with you in class, but as we are not meeting on a particular Tuesday, I'm going to give it to you as a video to look through. I'm going to go through this kind of quickly, and so if you need to stop the video and look back, you can do so that at your leisure. Also, there is a pretty good chapter, and I forget which number it is, but in that numerical methods for engineers book, there's a good chapter on discretizing partial derivatives, partial differential equations, and you can find other resources. A good resource is the book that you probably have used or are currently also using for your heat transfer ME 415 class. Chapter 5 in particular talks about discretizing. All right, so that's what it's called, discretizing. That sounds like a really fancy word, but that's essentially the numerical approach to solving partial differential equations numerically. So this is the heat equation, and you can see what all of the parameters mean here. Where this alpha is called the thermal diffusivity. You probably recognize this. It's the heat equation with a little twist thrown in here. This E dot gen, that is some energy generated term. I threw that in there because it's kind of useful. So we're going to solve this equation. We're going to do it numerically, and I'm going to show you how, mainly, the important thing to be able to do before we really start solving it is to approximate this thing here that I'm indicating with the arrow, that second derivative, partial derivative of t with respect to x, and this thing over here, the first derivative of t, temperature, with respect to little t, time. Right? If we can approximate those with finite difference equations, that is tantamount to discretizing the thing, and then that makes it relatively easy to solve. But we've got to be careful how we do this. Right? Also, this heat equation falls into the general category of something called a parabolic partial differential equation. Right? And it's a little bit tricky, just a little bit, because you've got a single derivative in time and a second order derivative in position. All right, well, there's another version of the heat equation. It's called the Finn equation. It's really just the same thing. The heat equation, you can see this term and this term that I'm indicating by the arrow are the same, but instead of a generation term, we've got a heat generation term. This is a convection term, which happens because the fin, or the part that plays the role of a fin, the part of the system, is in contact with a fluid most of the time. It's the atmosphere. And so you just throw in this convection term and you go from the heat equation to what's called the Finn equation. That alpha is the same thing, thermal conductivity K divided by the product of the specific heat and the mass density here. So these are the two equations we're going to solve. All right, and so let's go into the numerical approach. All right. Now, I showed you recently the importance of Taylor series, and you may want to go back and look at those slides. By the way, these slides are already under the resources tab under our you know what I mean, our course site. All right. So you can get to all these slides also. If you want to. But it might be worth going back in the slides and reviewing the Taylor series also. So just quickly, like I said, I'm going to go through these quickly. If you need to stop it and look at it and stare at something, or maybe do a little bit of algebra yourself. I'm not going to do all the algebraic steps here on my slides, but it's not that difficult. I'll skip a couple algebraic steps. You might want to stop the video and do it yourself just to convince yourself that I've got the right expressions. All right, this is a Taylor series. It's an infinite series, right, of some function expanded about the point x0. All right, so we're considering the neighborhood, mathematical neighborhood of x0, delta x, all right, and that's an arbitrary value at this point. And it produces, as long as these terms, as long as the series converges, then this is an exact equal sign as long, with an infinite number of terms. All right. So if we truncate this, now we've talked about truncating before, and that literally means we lop it off. So if we truncate this series after the first term, the equal sign then becomes this little wiggly approximately equal sign, right? And we come up with this expression here, which can be solved very easily for the first order derivative of f with respect to x. You'll recognize this. This looks a lot like the simple Euler form, right? Now keep in mind, at this point we're working with total derivatives. These are not partial derivatives. The jump to partial derivatives and approximating partial derivatives will be made at the very end here. And you'll see how easy it actually is to make the jump. But we start with the Taylor series, and truncating after this first term gives us this expression for approximating a first order derivative. Remember that the accuracy is given by the order of magnitude of the term we lopped off. And by the way, this is a type of approximation called a forward difference equation. It's called forward difference simply because I'm evaluating the function f at some value x0 plus delta x, which is a higher position or a forward position relative to the function evaluated at x0. Right? So that's where we're going forward. It's a forward difference equation. All right, so keep this one in mind. Keep this forward difference equation in mind. That's going to be one of our approximations, right? Now, from here to the next slide, I'm going right back to the same Taylor series, right? And here we're going to generate another type of approximation, right? So this is a Taylor series for f about the position x0 again. You can see I am approximating x0, the function at x0 plus some neighborhood delta x equals all of these terms here. Look at this next term, or this next expression underneath, and you'll notice the only difference is instead of x plus delta x, I've evaluated the function at x0 minus delta x. Now this doesn't change the generality of the validity of the Taylor series. There's nothing different about adding a negative value. And so you can see what happens in the odd ordered terms here. You have now a negative sign showing up. So the difference is I'm x0 minus delta x rather than x0 plus delta x. And you can see on the second term here, we have a minus sign instead of a plus sign, and the same over here, and so on. Every other term will have a minus sign in it now, right? So the next thing we do, and you can see what it says here, it says subtract the second equation above from the first. So you simply take this first equation and you subtract the second one. That means you take the left-hand side, subtract this equation, and then everything on the right-hand side minus everything on the right-hand side of the second equation. And this might be where you want to take a moment, stop the video, get out a little piece of paper and do the 2 or 3 lines of algebra it takes, just to convince yourself that I have written down the correct expression here. Right? Basically, I think you can see what happens if I take this first equation on the right-hand side, subtract from it all these terms in the second equation below. Clearly, these positive terms here and these negative terms here are going to cancel. So this term will cancel this one, this term will cancel this one, and so on. We still end up with an infinite series, but these are the terms which are left. And actually, if you subtract this, all right, the minus sign here, I didn't say that right, actually. I made a mistake in the description, so let's back up a moment. This term here cancels this one because we're subtracting all this stuff. We're subtracting the stuff on the bottom from the right-hand side of the stuff on the top. All right, so I apologize for being confusing there. It's actually these terms which cancel each other out. If I take this term here, delta x times df dx of x0, and subtract a negative from that, that's actually the same as adding those together. That's why we have the factor of 2. And the same with this term. You actually have 2 times these. Take a moment and convince yourself. It's simple algebra. We're simply subtracting the lower one from the upper one. So take a moment and convince yourself. All right. Moving on. If we take this, we still have an infinite series that results. And now what I'm going to do is truncate it after this first term on the right-hand side. That means we're lopping off terms of order delta x cubed and higher. Oops, didn't mean to go forward yet. And so you can see what results here. Right? So I've got the left-hand side, and I've truncated on the right-hand side, so this exact equal sign turns into a wiggly approximation. And look what I end up with here. See this? I have an expression which involves df dx, and on the next slide, I simply solve for, where's my arrow? I simply solve for this derivative. And so from here to the line at the top of the next slide, there's a few lines of algebra, and it might be worthwhile again to stop and convince yourself, go through the little bit of algebra it takes to get to this. This is what I was wanting to arrive at, and this is called a center difference equation. Now what you might want to do is go back about 2 slides, I think, and compare this approximation for a first order derivative with that forward difference equation. The forward difference equation was f of x0 plus delta x minus f of x0. You can see why this is called a center difference equation. Look at the numerator here. This is symmetric now about f of x0. This is f evaluated at x0 plus delta x minus f evaluated at x0 minus delta x. And you have a denominator of 2 delta x. This has an accuracy of order delta x cubed. I'm going to go ahead and go back a couple slides just real quick. Remember, the forward difference equation has accuracy order delta x squared. So the reason I took you through this calculation here is to show that the center difference equation, the center difference approximation for a first order derivative, is actually more accurate than the forward difference equation. Right? Now, keep in mind, the big picture, we have not yet approximated partial derivatives. That's coming, but I just wanted to show you the form of the total derivative here. Right? Now, let's go back to something we did. Again, go back to the Taylor series. So once again, here's our starting point. This is a Taylor series expanded, f expanded, about some arbitrary position x0 plus delta x, and you can see what results for the infinite series. Right? And let's write down the exact same thing we did on 2 previous slides. Once again, instead of x plus delta x, I write down x minus delta x. Now what we did before, you may remember, I took this first equation minus the second equation. Now we're going to add the 2. As it says here, it says now add the second equation to the first. Right? Now, I hope you can see, this is a little easier to look at, that it is indeed this term and this term that will cancel out, as well as these odd ordered terms going out on the infinite series. So this delta x cubed termed here, if I add this side to this side, this term will cancel this one. The delta x to the 5th power term will cancel in each case. And you can see we're left with these even ordered terms here. Right? So f of x0 plus delta x plus, just doing what it said to do, f of x0 minus delta x produces another infinite series, but some of the terms have canceled out here. Right? Now what do we do here? Once again, we're going to truncate it, but now I'm going to hold on to the first 2 terms on the right hand side. Right? So we truncate after, well, this says after the fourth order term. This is the 4th order term. We're actually truncating after the 2nd order term. So we're truncating terms of delta x, order delta x to the 4th and beyond. So this isn't quite stated quite right here. Right? So in other words, we're holding on to the 2 terms on the right hand side. Right? And I think you might be able to see what we're after here. This allows me to solve for this derivative, a 2nd order derivative of f with respect to position, or some independent variable x here. Right? You can see everything else, the terms on the left hand side and the other term on the right hand side, involve the function itself, And so this gives me a way to approximate the second order derivative, which I do at the top of the next slide. After about 2 lines of algebra, I can approximate the second order derivative of f with respect to x as this finite difference equation. It's a little different looking centered difference equation from the previous one we produced, because this now does have f of x0 in it, but you can see it's symmetric about x0. Evaluate the function x0 plus delta x. By the way, it's a minus 2 here, take note. F of x0 plus f of x0 minus delta x. So it's again centered about the position x0, and in this case the denominator is delta x squared. This has accuracy of delta x, accuracy of order delta x to the fourth. Once again, because if you look at the previous slide here, this is the term we dropped, this term and higher order in delta x. That defines the accuracy, right? So, what do we do with all this stuff? Well, let me go back 2 slides real quick. Okay, here's that center difference equation. Now, this is a center difference equation for a first order derivative, df dx. Let me go forward 2 slides after all that stuff. This is a center difference equation for a second order derivative. Now remember the heat equation. Let's go back, not go back, it's another slide, but I want to bring up the heat equation again. The reason we went through all that Taylor series stuff is to come up with a way, once again, to approximate a second order derivative and approximate a first order derivative, and we wanted to do it in such a way that it gave us the most accurate way to do it, right? So this is where now we make the transition from total derivatives to partial derivatives. Look at the heat equation. I think it's clear that there are actually 2 independent variables here. First one is x. So position is an independent variable. In other words, T, temperature, capital T, depends on position as well as time. So T depends on 2 independent variables, x and t. All right? And so here's where the partial derivative comes into play. We're going to approximate the derivatives. Which derivatives? The derivatives in the heat equation here, which is this term and this term. We're going to approximate these as usual with finite difference equations, as it says here, based on what we just did in the previous slides in the Taylor series expansions in the algebra we did manipulating them. So here's what we're going to use. We're going to use a forward difference equation for the first derivative here. Now remember, we went through and used the Taylor series to derive a total derivative, but look what I'm doing here. I'm actually making this a partial derivative, but partial derivatives are easy. We just pretend, look at this, see this? T of x, t plus delta t minus t of xt. I'm pretending here for the derivative of capital T, temperature with respect to little t time, I'm pretending that x is a constant, and that's how you deal with partial derivatives. It's the easiest thing, so that the forward difference, oops, didn't mean to hit that, the forward difference involves only the time variable here. So the first order partial derivative of temperature with respect to time involves the temperature at some generic position x at t plus delta t minus t at that same arbitrary position x and at an earlier time. Right? That's the jump from the total derivatives we came up with in the Taylor series analysis to the partial derivatives here. You just pretend that the other independent variable, in this case x, is a constant. Super simple, right? And we're going to use the center difference equation for the second order derivative. And in this case, it's the second order derivative, partial derivative of temperature with respect to position now. That means we're going to pretend that the time independent variable is constant on the right hand side. So you can see the center difference equation, x plus delta x, x minus delta x, and x. So everything's centered around x here. All right, again, if you want to stop the video, you can look back and take a peek at how I arrived at these. But the jump from a total derivative to the partial derivative is very easy. So the next step, once you understand, and make sure you do understand where these things came from, this expression for dt on the right hand side is going to go here, and this expression down here for the second order derivative with respect to position, this stuff over here on the right hand side is going to go over here. You just simply take these expressions and plug them in, right? Now, what's next? We're going to rename things, all right? And this is what we did when we were doing back the simple Euler and the Runge-Kutta methods for solving ordinary differential equations. We're going to use an index, and in this case we're going to use a time index. I'm just going to arbitrarily call it I. But remember, there's two independent variables now, t, time, and x position. So I need a space index now. So I'm going to call the space index m. So we're going to rename things from this bulky notation here. Instead of x, t plus delta t minus t of xt, we're going to use this notation now for the space. M is the space index and I is the time index. Now don't be confused by this notation. You'll notice it looks like I'm raising temperature T to the I plus 1 power. This is not an exponent. This is just a superscript that that keeps track of the time. All right, so please keep that in mind. Down here in this one, I is not a power that T is raised to. This is just another way to indicate the time index. All right, so this is the renaming of these approximations for the partial derivatives. And because they're finite difference, and because we are only going to be coming up with solutions at discrete times, I, or discrete indexes I, time index I, and discrete position, oops, where'd my arrow go? Discrete position M. The discrete, that's the root word of discretized. So these are the discretized versions of these partial differential equations. All right, now what we're going to do, as I said, let me go back one slide, we're going to plug those in here into these derivatives, and that's going to be the approximation, and we should really turn this into a wiggly equal sign once we make the approximations here. Before we do that, let's talk a little bit more about the numerical approach. All right, so this is we're going to be solving the one-dimensional heat equation to start with. In another project, we're going to tackle the two-dimensional system, but we'll save that for later. So here is an effective 1D system. This blue color is meant to represent a continuous material, all right, between some position L, the left-hand side of whatever this is. This is a rod or a bar or something, and we're going to study the heat conduction in this thing. The left-hand end of the thing is at 0. The right-hand end is at position L. All right. But here's what we're doing. In making the discretized approximation, we're not finding a value of the temperature for every time at every position along here, at every continuous position. We are only finding the solutions at discretized times, at discrete times, at these discrete positions represented by these dots. These dots are supposed to be points in space, right? So we are only finding the solution to the heat equation at these discrete positions along the rod, or whatever the system is, at certain times, right? So there's a couple things we have to think about. All right, each of these discretized spatial positions are called nodes, right? So if the node is not at a boundary, by the way, that's what this is called. You probably know this already. X equals 0 and x equals L are the outer boundaries of whatever this material or system is. And the nodes, which are not at the boundaries, are called internal nodes because they're internal to the system. And these ones on the ends are called boundary nodes. Right? So this is some of the nomenclature we got to get down. All right. If this is the mth node here, now remember we're starting out in one dimension, then, oops, if that's the mth node, then the one to the left is the m minus 1 node, and the one to the right is the m plus 1 node. And as we number things and keep track of these, it's good to index things like this. We've already renamed it in terms of these indexes, but that just makes it easier to also cast the problem in a form that can be allow us to use a computer to do all the computing for us. If that's the case, then the left-hand boundary is the m equals 0, the 0th node. So we're going to apply m equals 0 to the left-hand boundary. And however many total nodes there are, we're going to let the node out here at the right-hand boundary be the capital M node. Right? So we've got total m number of nodes spread, actually, I take that back, capital M plus 1 nodes because we started counting at 0 here. This is subtle. Keep that in mind. If we call the boundary node the 0th node, there's actually capital M plus 1 total nodes. All right. The distance between each node is some fixed delta x if we space these equally. That's just the total length of the system divided by the number of nodes we have. All right. Thus, we have a finite difference 1D heat equation with a source term. And all I've done, you can convince yourself, look back a couple slides if you have to. This is the heat equation. And I've taken my indexed approximation to the second order derivative of partial derivative of temperature with respect to position here. That's what this term is. Plus E dot M. Now, that E dot generating term, I replaced the GEN with an M because we will be considering heat generated in node M here, divided by this constant K. Right? And then here, over here, is the approximation to the first order partial derivative of temperature with respect to time. And you can see this is that forward difference equation I'm using. If you do a little bit of algebra from here, and I think you can see that it's not too much, you come up with this expression here. And look at this. The only term in this expression here at a later time, now remember the superscript I is the time index. This is the only term right here that involves spatial step or spatial position M and a later time. I plus 1 means 1 delta t later than time I. This is the only term that represents a later time. Everything else in here is at the earlier time. See that? Therefore, it's really easy to solve for the temperature at node M, spatial node M, at a later time I plus 1. That equals then this tau, which by the way is given by this after you do a little bit of algebra. Again, stop the video and do the 2 or 3 steps it takes to convince yourself this is correct. Right? There's a combination of the temperature at the earlier time at the node to the left of M, to the right, M plus 1, plus the temperature at the node to the left at the earlier time. Then another term here involving that tau at node M at the earlier time, plus this constant term, actually. And this tau has a number. It's called the Fourier number, and that plays a special role, which I'll mention in a moment. Right? So this is the discretized heat equation in one dimension, and you can literally use this equation if you know the distribution of temperatures across the spatial nodes at the initial time. You can use this equation then to march forward in time and calculate the temperature at node M at the later time. And then all you have to simply do is run through all the nodes, because you can see that for each node M, to calculate the temperature at the later time, it's sort of a weighted average of the node to the left, the node to the right, and the node itself at the earlier time. Right? Plus this constant term here, which depends on any energy generated at some node within the system. Right? This is called the explicit scheme. That's what you call it. It's called the explicit numerical scheme for solving this heat equation or this particular parabolic partial differential equation. And your project number 4 basically guides you into doing that. Now, a little bit later, we're going to do another project, and so it's not so important to spend any time thinking about what I'm about to show you at the bottom of this slide. Looks like I'm having fun with PowerPoint here. if we were to use a backwards equation for the time derivative, then the equation looks a bit different, and it actually is an entirely different algorithm called the implicit scheme. Don't worry about this now. We will come back to this implicit scheme. If you try to look at that now, it might be a little confusing. Don't worry about it. For now, focus on this explicit scheme. It's a very easy equation to use to march forward through time and calculate the spatial temperature distribution across all the spatial nodes marching forward in time. All right. One more slide, and then we'll call it good. So this again is the forward difference equation that the discretized heat equation. All right. There are two difficulties that have to be dealt with, and I think the best thing to do is for you to start trying to implement this in the project that I have, and you'll see how this comes along. But I want to warn you, there's two things you've got to be very careful with. One, when you deal with the boundaries, and so let me just point something out here. Let's say you're trying to find the temperature of node number 1, so let's say m is 1, at some later time I plus 1, where I is some generic time step, right? Well, look what happens. If m is 1, if you're trying to find the temperature at node 1, well, this first term is okay because that says use the temperature at the earlier time of node 2. 1 plus 1 is 2. But look what happens here. This actually is 1 minus 1. That means you have to take into account the boundary. All right? Now, it's okay for node 1 because you're just pointing, m is 1. This just simply says 1 minus 1. You may remember we called the 0th node the boundary node. So we actually do have a temperature we can use. But what if we're actually trying to calculate the temperature of the boundary? Okay, we've got to be careful how we deal with boundaries. What if m was 0? If m was 0, well, this term's okay. But look what happens. 0 minus 1. There is no node 0, or there is no node t position minus 1. Right? So you got to think about how you're going to deal with that. And I'm going to, at this point, kind of leave it to you a little bit. It's actually not that bad, but you guys got to be careful. The other thing is stability. All right? And if you want to read a little bit more about this, there's something called primary coefficients. This is dealt with in, I believe, that chapter 5 of the book you use in your heat transfer course. You might want to look it up there. But this term here, so what we mean by the primary coefficient for this equation, for this particular version of the heat equation, is just this 1 minus 2 tau. It's the term that multiplies the temperature evaluated at node m at time I. That's called the primary coefficient. That has to be greater than or equal to z. I'm not going to prove it to you. It's actually not complicated. It's a little bit of an eigenvalue problem, but don't worry about it. I'll just show you the result. 1 minus 2 tau has to be greater than or equal to 0, which means tau itself. Now, this is actually a unitless quantity. This number, tau, the Fourier number, has to be less than a half. So that's something else that you have to be aware of and be very careful of when you're implementing this thing called the explicit numerical scheme. All right, well, that's all for now. That should get you going. Like I said, go through this. Take time if you have to, if you want to look back and understand a little more in depth the Taylor series analysis, although it really isn't difficult. We were just truncating the Taylor series and then doing a little bit of algebra to build these approximations that we used for the partial derivatives. All right, that's all for now. Please drive safely, and may the force be with you.